It's recording. Hello. Yeah, I wanted to share something I've been working on. So I was working on this actually about a week ago was the last time I really looked at it. Bar about 10 minutes ago. So it's neural network and KDB from scratch, from nothing. So I struggled with this for probably a couple of weeks. Let me show you, I've got many versions of the same script. Also, my scroll wheel is broken, so the screen's jumping around, which might be annoying. So let me just explain what a neural network is, and that will be easier visually. So we've got a small neural network here. It's got 5 layers, 5 inputs, and 10 outputs, and we can visualize that. So first we'll use the Q code to create the network. Then we can visualize it there's Python code behind the scenes here, which allows us to visualize it. So we'll do that. So here's the network it created. And if we zoom in here, we can see the inputs. So there's 5 inputs. 1, 2, 3, 4, 5. And there's 10 outputs at this side. And so information flows from the inputs through the hidden layers to the outputs. And at each step we can see that each input has a unique set of connections to the next layer, and each layer will only connect to the immediate upstream layer. There won't be a connection from the input to layer 2 or 3, only from the inputs to layer 1, and only from layer 1 to layer 2, and so on. And so what happens, so the inputs obviously change. In our case, we are giving the network images. And in each case, each input is actually a pixel value. So the pixel values are it's a black and white picture. It's either pure white, which is value 0, or it's pure black, which is value 2, 5, 6, or anything in between, which is grey, I guess. And so this information is passed to the input layer, and as it's passed to the next layer, here's what happens. So if we look at a single neuron in the next layer, we can see that it has multiple inputs. So it might take maybe a subset of inputs. In the actual data, there are 784 inputs, not 5 in this case. And so what each neuron will do is take all of its particular inputs and apply an activation function. So that activation function can be one of many. If we look in the code, there are different activation functions. But basically they take the input values from each input neuron, and it decides whether that neuron will fire or not, or the strength of the firing. And so each neuron does that. This is done for each neuron, and that's passed to the next layer and next layer until we finally get to the output layer. But the important thing is the strength of the connections. So that's what actually changes over time, and that's what we call learning. So if you look at any one of these connections, each one has, and we call it a weight. Each one has a weight, and that's basically the strength of the connection. So this particular connection would have a particular strength, so that's a weight value, and over time that weight value is what's actually changed. When we load the code, we just randomly create weights, so it's just a random number between 0 and 1. It can be more complicated than that. There are actually other types of weight initialization procedures, like Xavier and He, and I actually implemented those as well and tried different ones. So we'll see that in the code. But that's what's actually changing. So what happens is we give the input, and we know what image the input represents, so we know what the output should be. The output should be 0 for each, apart from the number that it's supposed to represent. If the image represents the digit 0, then input 0 or output 0 should give a value of 1, and the rest of the output should be 0. So what we can do then is we know the expected output, we know what the network outputs, and then we just compare that to each other. We take them away. That gives us something called a gradient. So let's say it predicted a 1 when it should have been a 0, then that's a large gradient, a gradient of 1. Let's say it predicted 0.8 when it should have predicted 1, then that's a smaller gradient of 0.2. And so what we do then, you can see for each output we get a value of a gradient, and that gradient will inform how its particular weights should change. So that's what we call back-propagation. So what we do during back-propagation is we get the gradient for each neuron in the output layer, and we work backwards. So we update the strength of the connections, the weights, backwards through the network depending on that particular gradient. And we do that for each layer. And that process is called back-propagation. That's the major step. That's how the network actually learns and updates itself as it guesses over time. So when we load the code, the first thing that's done is we create a network. After we create the network, we run this analyze connectivity function, analyze sparse connectivity function. Then we create, this is a dictionary that represents the actual value output. So this is like when a neuron gets all of its inputs, applies the weights, the inputs, the activation function, the bias, it will give a single value whether it fires or not, or the strength of the firing, which is between 0 and 1. And then we have another dictionary that represents the pre-activation function values. So this net v, net values, is the value of the neuron after it's been activated. Net pv is the value before we apply the activation function. And in our case, we're using GLU, whatever you call it. We have a dictionary here called net weight. So this is every single connection, value for each connection. This is the actual weight initialization at the start, and you can see it's just random. So I do small weights. I find this to work quite well. So it's kind of random at this point in time. I can change that and it will learn. It will learn if I change the activation function, if I change the weight initialization, the bias initialization. Let me just reference what bias is. I don't think I went over that. So as I said, each connection has a particular strength. So each one of these connections has a particular strength, and that's what's being changed over time. But also each neuron has a particular bias, which is a value that it's different for each neuron, and it can actually change over time. And it depends, it's kind of saying how likely is the neuron to fire. So some neurons might have a big bias, which means they take very little input to actually fire. Others might have a small input, a small bias, which means that their inputs must be large in order for that neuron to actually fire. So that's just another consideration. It still works without the biases, but it's typical to include them, so I included them. And I guess in general, in what I'm saying, it's kind of wishy-washy. You can change a lot of things. You can change the activation function. I think that means that in general, it's this whole holistic process that allows the system to learn. The specifics don't seem to change things much. It still learns. And those are just tweaks. I think, what do they call it? I forget, there's a technical name that people use for this. Choosing the learning rate decay, the weight initialization, number of layers, number of neurons. This is all tweaking, hyperparameter tweaking. So that's what we call them, but they're hyperparameters. In general, this just works. Okay, so we load the script, it creates a network, it initializes the weights and the biases. Then we load the images. In this case, we're just doing the mness numbers. So this subset has 100,000 images. We calculate the expected outputs. So when we load this data in, we can look now. So the first image represents the number 1, and we can take a look at that now. So we have a function to view these images, a Python script I wrote. So we can just push the image to, let's do the first one, so let's do this image. So this is last images 0. And then we can view it with this function, with this Python script. And you can see it represents the number 1. We can look at a different one. So this one should represent the number 2. So we'll look at that. And so that's the number 2. Let's look at number 4. So 0, 1, 2, 3. So for every single image, we have the expected output, what it should be. And that's what we use to compare between the actual guess each time and the actual output we know it should be. That gives us gradients that we can then push back propagate through the network to update the weights and biases. We have some code here just to collect statistics as we go along, like how many it's getting correct, and there's the actual how far away so if we look here, we can combine all of these values to get a total error to see how far away off it is. So it should get smaller and smaller and smaller. These, in this case, all of these should approach 0, and this should approach 1. And that means the network's learning. And finally, we pass each image and each expected output into the train network function, and that begins training. So the first time this runs, obviously the batch will be this batch will be 0, and it's reset after every batch. So it will do, this batch will be 0, it will keep going, and then it will reset once it gets to the actual batch size. Okay, so once it reaches 28, once it runs this function 28 times, after 28 images, it will reset this batch to 0. And so this is updated after each batch. So this is just an object that holds the new weights, what the weights would have been updated, what value the weights would have been updated to, and what the biases would have been updated to. And so we hold 28 of those, and after the batch we actually apply the update. So we just do the average of them. You can see that here. So we have logic to update the weights. We update the actual weights of the network, and we update the actual biases of the network after each batch. And we can see here we apply GILU to every layer apart from the last layer, which is we use a softmax. And here is the actual code that fires the network, that actually propagates the image through each connection, uses the weights and the biases for each neuron, and calculates the output, passes it on to the next layer until we finally get an output. And at that point we can then compare the output to the expected output, which is what we do next. And you can see here we just use the calculated outputs, what the network guessed. We compare it against what we know it should have guessed, and that gives us gradients. And we push those gradients, we propagate those gradients backwards through the complete network, and update each, we actually get a value what it should be updated to, the weights and the biases. And then we just do some calculation about did it get it right or wrong, and we store that in a global list called correct or loss. And this is how we actually see the progress of the model over time, how it learns over time. So let's actually just run the thing and we'll see how it does. So it has created a network and now it's running, and we have some Python code to view this loss over time. And so we can see here the loss is decreasing over time. That means each output is becoming more and more similar to what it should be, what we expect it to be. And we can look here at the code as it runs and see the accuracy. So we've just been running that for a few minutes and we can see it's up around over 80%, 90% accurate. So let's let it run for a little while and we'll see how high we can get this thing. So I actually let it run for a little bit longer and it got up to, it says 100% accuracy. So I'm not sure if that's correct. We would have to run it on many, the whole test set. This is just a subset, like the past 200 or 100 images, how many it got correct. So in this case, out of the 100 images it's seen, it got all of them correct. But it should be a similar value. So we'll test it on images that it hasn't seen. So in this case we can see this is a 2 and it guessed 2. So that's correct. This is a 4 and it guessed a 4. This is a 7, it guessed a 7. This is a 2, it guessed a 2. It's a weird 2. This is a 6, it guessed a 6. This is an 8, it guessed an 8. Maybe it would be actually interesting to run this on a lot of images to get the true accuracy of it. We're going slow here, we're just looking at each individual, but we can do it. So let's do that. Let's go to the code. We'll just try it on one image first. Okay. And it should be returning a value. Okay. So we're going to run it on those last 20,000 images that it has not seen. And we'll see how many of those it gets right. So results is empty now. Okay, it's an empty Boolean list. And then we'll run this for each of those 20,000 images. Okay, so we're finished. So we can see the actual accuracy now. So results should be a list of 20,000. So this is the results for how it guessed, how our network, after we let it train and learn, how many it got right or wrong. So count, let's see, sum. So it got 19,150 correct out of 20,000. So yes, sum results divided by count results. So it says it's actually 95% accurate, which is pretty good. So with a little code, we have built a system which allows our computer to see a handwritten image and tell us what number it is. So that's pretty cool. And this is a sparsely connected type of neural network setup. And this code, I could probably put this up on GitHub. I will have to change I've got a lot of extra scripts. I've got, let's see. Yeah, I've got like 10 versions of this. And even then, I just got it to a point where it works and I got reasonable accuracy. But I've got ideas on how to make it more interesting. And I've got other use cases for it. It works on the digits and the numbers, but I think I can do other things with it. And this is all Python code, and I'll upload that as well. So you can visualize neural networks. And just be careful, you can't visualize massive neural networks. You have to make them quite small for the browser to be able to handle it. But this is just good to be able to visually see that, everything has a connection, things aren't connecting, forward layers, stuff like that. Like input, one of the inputs shouldn't have an input because it's the very first input. An output shouldn't pass on to something else. Things like that. That's why I have this, that's why I built this. Yeah, that's all I have for now.